So, well, I would like to welcome everybody who is present at this seminar of the Sano Center. And today we start two seminars on Sano Center research agenda, which at these seminars will be presented by Dr. Arkadiusz Sitek, who is director of Sano Center. And somebody may ask why just now, uh, while Sano Center is in operation almost 1 year and a half, more or less. So I would like to explain why. First of all, uh, to become a director of the Sano Center is not so easy. We have a procedure and well, important point of this procedure is evaluation by uh, International Scientific Committee. International Scientific Committee of Sano, if you could, is composed of 15 well-known, recognized persons from both from computational medicine, from medicine, and from computer science. And it was quite a serious competition. We had a number of candidates, and the process was going on, taking quite a time in order to find the first decision. And the decisions were the following. If you could. So first of all, Arkadiusz was elected by International Scientific Committee as the Sano director in the middle of May 2020. And from that time, Arkadiusz has started to work together with Sano team on research agenda, improving and modifying in considerable way what was presented in two uh, research proposals on for teaming and for international research agenda. And then there was a process of acceptation of a director by Polish Foundation for Polish Science. It took place in the middle of October. Then on just before Christmas, Foundation Council of Sano took decision on employment of Arkadiusz. And Arek started his duties on Wednesday previous week. So it is something like fourth day of the operation of Arkadiusz. And shortly, I would like to just to tell a few words about his CV in short. So first, well, Arkadiusz has completed his studies in 1994 at Warsaw University, but just after that, he spent all the time in outside of Poland. So first of all, he spent 15 years in teaching hospitals in Canada and US. And then he was working as a researcher in industry. It was mainly Philips and IBM. And well, during this career, I think that the next slide will be very interesting for you. Well, you can see here on one slide his research activities after completing the studies. In short, you can find here what type of scientific methods were used by him and where he was working. So he started from molecular dynamics applied to cardiology, Then it was simulation using Monte Carlo, statistical methods for neurology, and finally, when he was working at Philips and IBM, it was machine learning, artificial intelligence. And you can find also logos and names of institutions at which Arkadiusz was working. So we are very happy to have such a director at Sano, because, well, it's not only his research experience and broad area of research interest, but also it means that Arkadiusz is bringing to Sano contacts and collaboration from US and Canada. So it is a complementary to what we have, because we have our, let's say, contacts and research opportunities in Europe. So in this way, Sano has a kind of potential to become globally known. So it was a short introduction. Now, floor is yours, Alex. So.
Thank you, Marian, for this very nice introduction. And I'm just going to switch now to my presentation, which is titled Artificial Intelligence and Computing in Medicine, and why, how, and when. So first, I would like to acknowledge our funding, which comes from European Union Horizon 2020 program, from Foundation of Polish Science, as Marian said, but also from Polish Ministry of Science and Higher Education. Very quickly, Marian already mentioned this. This is a first seminar in a series of 2 seminars. The seminar is going to be about using computing in medicine. And in today, I will tell you a little bit about why we want to use computing in medicine, and how we're going to do that, what kind of techniques we're going to use. And also I will tell you when we'll see some effects of those activities. And next week I will concentrate of particular activities that Sano will take towards those goals of impacting the healthcare. So the plan of the presentation is pretty easy. There are 3 parts of it, and the first part is going to explain why, then say hi, and then say how we're going to do that, and finish with the estimation of the date. Why? Well, I'm going to start with providing you with this title of the publication from British Medical Journal from 2016, that medical error is a third leading cause of death in the US. So for anyone who basically maybe stops for a second and think about it, that's actually very significant statement. It's actually preventable medical error. So at this point, if we think about it, that's a reason good enough to try to do something about it. And I think computing and artificial intelligence may actually help. Just very quickly, what are the medical errors? Well, for example, wrong procedure, or medical procedure not done as it should be done, or human errors, or things like that. Obviously, there are some other issues that are also very important that computing can help with. For example, a shortage of doctors that's everywhere. We basically don't have enough medical personnel, and it's I said doctors, but it's not only doctors. Medical personnel, like for example nurses, is a very similar problem. The burnout, it's associated with the previous problem, simply because there are shortage of doctors, they are overworked. You know, they actually have things to do that very tiresome. So the actual contact with patient is not that is not the first in terms of the time they spend at work, and that is associated with very worrisome level of depression in doctors and medical personnel and so on. And everyone knows the third point here is the chronic conditions, health chronic condition. This is unbelievable. You know, if you think about it, you know what's going on. There is just think about our children. Right now we have diabetes. You know, rampant diabetes, ADHD, autism. These are the things that we shouldn't tolerate as humans. There are other things like late-term care that is also very important problem for all medical systems in essentially all developed countries. How to deal with this issue, and not the least one, but also very important, is the cost. You know, that healthcare costs a lot of money. That money can be invested in economy in a different ways, more maybe productive ways. But unfortunately, it's tied to healthcare, and that's something that we also have to think how to change that, how to make healthcare less expensive. Just about the cost, you know, I brought this slide where I show the data, the life expectancy in years at birth versus the spending per capita, and different dots on this graph correspond to different countries. And as you see, you know, throwing money at healthcare, at least based on this graph, does not extend the life expectancy. Well, it's obvious. I mean, we cannot live 200 years, but at least, you know, why it may not be, you know, the best surrogate life expectancy to judge whether the healthcare works, but the obvious question may come, you know, well, why do we spend so much money if we can spend, for example, you know, before reaching the plateau in this graph, you know, and then maybe you cannot improve more by throwing the money at healthcare systems. Very interesting is also here the USA, which is one country that I marked where spending is the highest by far from all countries, where, for example, life expectancy is not that great. So one question could be, you know, if we put the trend line into it, well, maybe actually spending more money is not beneficial, but opposite, it's detrimental. So obviously, you know, after saying all those things, we also have to acknowledge that healthcare has also good sides. You know, there are some miracles that the doctors do every day. It just you know, pretty amazing, but then those problems that I mentioned here, you know, they have to also be always on our minds. You know, sometimes when we are in the system, we are in the box, we don't see them, and sometimes it's good to just stop in what we are doing and think about all those facts that I said. Look at the state of our healthcare from outside of the box, and it's difficult, but one way to do it is maybe if we can travel in time, let's say 50 years in advance, and look at, you know, our healthcare in 2070, you know, probably then people will know, you know, what was wrong, and they, you know, they will say, well, how those people could do such things, you know. And just to tell you how this can look, you know, in 2070, how our healthcare look, well, we can look what was happening 100 years back, you know, what kind of healthcare we had 100 years ago. And obviously 100 years ago, it may look like you know, people had reasonable healthcare, but from the perspective, it right now doesn't look so great, you know, if we look at some things that were done at that time. So I hope I convince you that there are problems to work on, and there are problems in healthcare that they are there to solve. Now, how do we do that? So that's a very short slide. And one of the possibilities is to consider the artificial intelligence and data, which makes a lot of strides now in many industries. It's changing how the many things are done, right? So we, for example, we are probably looking at autonomous driving cars in some future. So that's pretty amazing, and those kind of inventions and innovations should also come to healthcare to help with all those problems that I mentioned. So this is, of course, assumption, but that's where I think Sano will go. And I will talk about particular and concrete steps that we're going to take in Sano to achieve this next week. Today, I wanted to tell you a little bit about this emergence of these amazing technologies that people called AI or artificial intelligence. But what that is actually, the machine is a part of the machine learning field called deep learning and use of the artificial networks. That's actually what made it happen. And obviously some other conditions like data. There is a lot of data that humans are generating now. This data can be used for many different reasons, and it can be used in healthcare. So, this facts, made that this AI is everywhere now. We see it everywhere, and we're gonna see it in foreseeable future. So I'm going to, for the rest of the segment, I'm going to explain it to you how actually this works, so how the artificial intelligence works. So for those who already know, I'm sorry, it may be a little bit boring, but I think there is a lot of people that may benefit from it. So I'm going to do it. I'm not going to go into the math, but just gonna take and do my best to explain it to you without it. So how the AI works is that there are three parts of it, as you see here. So on the left, I use mammography image, which is an input. And I'm going to talk a little bit more about it later. Then we have our processing unit, our brain, artificial intelligence brain, which is to decide whether there is cancer, the patient has a cancer based on this image or not. And then, so basically the output from the artificial intelligence in this particular case would be either no or yes. And the output looks like it's typically given in numbers. Well, it's a computer after all. And those numbers are typically from 0 to 1, means 0 means, well, we are, so if we, for no, we say it's 1, we are sure there is no cancer. If it's 0, that means, that yes is 1, that means that we are sure that there is a cancer. Yes and no, those numbers have to add to 1. So essentially, we can just say whether there is a cancer and express it with the number, and we will know what the value for no is. So, and this is a very important slide. What we need to understand, what the images are, what we provide to the algorithm, are just the arrays of some numbers. So what we see is also can be shown by the array of numbers. And for the mammography image, these images are roughly 2000 by 2000. So we have 4 million numbers. And then, and here, I'm going to make a very important statement saying that I give the example of the mammography image, but data are also arrays of numbers. So I will be talking, how the AI and deep learning works based on the images, but always mentally you can place, instead of images, some numbers that we get from, for example, healthcare system, from the tests that patient has, or from, for example, this kind of data could be the physician's notes, that the physician wrote about the patient, some statements, his impressions, that can be converted also to numbers and then processed by those systems. So the images are data, but there is a lot of different types of data in healthcare, which can also be processed by those systems. So now I opened, what we know, we have the arrays, which is the input, and then we know what the output is. And now I opened what's actually inside of this artificial intelligence brain. And what's actually inside this is there are arrays too. Those arrays, you can think about them like they are empty images put there. There could be many of them. Many of those layers could be there. Well, that's why we call this deep learning, because there are many layers. Could be the number of those layers could reach hundreds and so on, very deep. And then, of course, we haven't done anything. We haven't done any intelligence processing yet, artificial intelligence processing yet. So what we have an array with the numbers on the left. We have those empty arrays, which is the neural network in the middle. And then we have the output, and we don't know what the output is yet. So another part of this artificial intelligence brain are the connections. So because we have those arrays, every element in array before is connects to every element of the array that is next in this order of those arrays. So we have the input that connects on the left. You can see the input. The elements connect to every element in the layer in the artificial intelligence brain, and so on. This continues until it reaches the output. What is important here that those connections are actually they can vary in their strength. Some connections going to be strong, some connections going to be weak, some connections may not even exist. And then I draw here to remind you that there are a lot of connections. So obviously I mentioned that this input array can have 4 million elements. If we have 1 million array in the brain, first array in the brain, you can compute quite quickly, that there are a lot of possible connections and so on. That's typically, actually, there's many connections we typically cannot handle that. So there are ways, we use in the artificial intelligence computing to reduce those numbers. But in theory, that's a lot of connections that we have here. And then we have arrays, empty arrays. We have the input that have numbers. We have those connections, and then we start processing. And the processing is done as follows. We essentially, take the array before, and then using the connections, we compute what are the influence of the numbers in that array, and then we compute the number when we put it in the next one. So in here, the example is that we take the input and then compute one first element of the first array in our deep learning brain. And we do that sequentially. We compute the second number and so on. And once we fill the first array in the deep learning network, we do this with the second array, and so on and so on and so on, until we actually fill the network with all those arrays in the network, in the deep learning brain, with the numbers, and then we also generate the output. And basically, that's it. So that's how it works. So we provide an input, we fill all those arrays, and then we ended up with the answer. And in this particular example, the answer is, well, there is a 12% of yes of some question that we asked, and 88% of no. So this is the mode of operation of those deep learning networks. It's not much to it. If you conceptually think about it, as I just presented. Obviously, there are many different complications and techniques and many different details that I purposefully omitted just to give you the idea how this the deep learning artificial intelligence that you hear about all the time works. Okay, so far I've talked mostly about how it works, but then what kind of questions we can ask to this type of networks. And here I put an old picture, purposefully old, because to give you an idea that as a data scientist, we have to deal with the quality. Data is never perfect. Real world data is never perfect, and then so we have to expect always that what we try to process gonna have poor quality, and this has to be always on our mind. And unfortunately, this is one of the activities of the data scientist, is to check the data and clean it. Well, that's that kind of life data scientists have. But once we have this picture, what, for example, we can ask is, we look at this picture and can ask, okay, is there a baby in the picture? And then, we supply this picture to this processing brain, and then it runs, and then it spits out the answer. 99% it's gonna think it's yes, and 1% no. Well, if this is actually good AI, it should be actually much more certain that there is a baby in this picture, obviously. But well, I want to just mention that sometimes it's not going to be that obvious, even for human. So that's one of the questions we can ask AI, about the pictures like that. So obviously, I told you, how it operates, but just want to spend a few minutes, tell you, how do we actually train it? Because obviously, if we just do it at random, those connections that I was talking about going to be sort of random, we're never going to have a good answer to it. And what the training means is that, in order for the network to tell us what we want to hear, for example, is there a baby in the picture? We need to come up with the weights, with those weights of those connections. They are such that, well, the network will be working as intended. One of the parallels that we can draw here is that, when we start with training this artificial intelligence network, we start with the tabula rasa, empty arrays. There's nothing, there's no connections there. We start to build them. It's like a newborn human brain that needs to be trained. And that's what we do in data science. We train the network, means that we come up with the values with those weights, such that the network operates as it intended. And this is done, in very, I would say, silly way. Which is depicted in here. We basically repeatedly show to the network pictures with the babies, and then or without the babies, and then we modify a little bit of the weights to such that the network give us answer which is a little bit better than so for example, we show the picture with the baby, and then we obtain the output. We process, we obtain the output, and it's the x is a number for yes, 1 minus x for no. And if there is a baby in the picture, well, we modify those weights a little bit so the x is closer to 1. And that can be done. And then, of course, we repeat that many times with many different pictures. So then the network learns, how the baby actually looks in the pictures. It's a tedious process, absolutely. It's a very tedious process, and but that's how it works. So as I mentioned, in order to train the network to recognize babies in the picture, we need many different examples. One example is not enough because, obviously, if that baby is going to, hide behind the mom instead of being on her hands, it's the network will not recognize it. That's one of the problems with the current artificial intelligence, that they don't generalize very well. we need to actually provide many different examples of something in order for the network to generalize and then recognize this in pictures that it hasn't seen during the training. Also, what is important is not only whether we have a baby, but also the background. You know, if for example, we show, during training, we're going to show the baby always in the park, and then pictures without the baby is going to be pictures of the city. Obviously, the network will learn, you know, to recognize the park instead of that there is a baby in the picture. And then the next time when we try to apply this network to try to recognize baby in the city, on the city, when the background is the city, well, it will not work. So this is actually very important, and this is in medicine and medical imaging, but in medicine as well, because, and I'm just going to give you here an example. So let's say we trying to train the algorithm to recognize heart failure in the images from the X-ray. So so in order to train algorithm like that, we collect let's say 100,000 X-ray with no heart failure, with no enlarged heart, and no other indication of heart failure on the images. And then 100,000 of images of heart failure, but we collect the images of the heart failure from patients who were, while the patient were in the bed, while they were laying in the laying position, and then the pictures who are patients who doesn't have a heart failure were standing, where patients were standing. What that means is that actually the network can work perfectly, but it will not recognize the heart failure from the picture. It will recognize whether the patient is actually, in the horizontal position in bed. So we have to be very aware of those issues when we train the algorithms. It's very easy for missteps here. Another very interesting thing about training of those networks is, and I mean there are many tricks, but I just want to mention this one because it's very close to what actually humans are doing, because what works very well, for example, if you want to train the network on medical images, is to take the network that is already trained on something else. So if we train the network to recognize type of the flower, then the weights are set in this training, and we can actually take the weights as they were determined when recognizing flowers and readjust them to, for example, detect cancer in images. And it works much better than just starting from weights that they are random. I put here, it's like, it's easier to train, the radiologist who is an adult, to recognize the cancer than a baby that learns how to see. Sort of this transfer learning is a very important technique in the field, and it's used all the time. And now, one of the tasks that I was talking about, associated with the pictures, what we do is, I ask baby, but now I can ask a little bit more difficult question. Is there a toddler in the picture? So now the algorithm would have a little bit more difficult time, because toddler, not every baby is a toddler. So how do we recognize a toddler? Based on what? Another thing that we can ask is then an apple in the picture. So when we ask about the baby, well, the baby is quite big, and typically on pictures. It may be easier to recognize. But the apple in this example is pretty small. Typically, it's going to be very small. So this is also a task in what we need to deal with in medicine. That sometimes we have very little things that we need to find in the pictures. And the third task is something that I want to concentrate on for the rest of this segment, because we can also ask very like artistic question and ask, is that scene that you see here, you know, happy or sad? And obviously, you know, this different people may give you a different answer. So it's something that, again, we have to deal with in medicine, because the ground truth, if we just establish the ground truth based on people's impressions or the expert impressions, well, you know, many doctors can have very different opinions on things. So the same in here. People can have different opinions about, you know, whether picture is sad or happy. But what's more important is, you know, even if for example, I think, you know, the picture is happy, but then if you ask me, what in this picture make you think that picture is happy? Well, could be many things, right? So could be that it is in the park. You know, the park is typically, well, it's a happy thing. Well, there is a mother and probably mother and a son, so that's always brings happy thoughts. There are some smiles, but the baby doesn't smile. Babies, yeah. Well, so how this gonna affect, you know, assessment that the picture is happy? Well, it's a contradiction, right? I mean, well, what I want to tell you is that, you know, actually the hints about some things that we try to get from the picture can be anywhere. And it's going to be very hard to pinpoint what actually makes the human decide about things, and it's going to be very similar problem when the AI is at the works. And I'm gonna, you know, talk about it a little bit more because it's a very interesting problem. I'm just gonna go dive a little bit deeper into the problem into the mammography. So the mammography, as probably you all know, is a very successful cancer screening program, and we use X-ray that goes through patients' breasts, and then depending on attenuation of those X-rays, the picture is going to show some texture in the breast. So abnormal textures, abnormal consistent with the cancer, will gonna be detected by typically the mammographer, and he's gonna decide, okay, there is a high chance that the patient has cancer. So basically, the mammographers are looking for these abnormal patterns. There is actually quite a bit of research done on this topic, you know, when using those new technology, those AI. And just giving you one example here, you know, the performance actually in detecting the cancer is now very high by those algorithms, you know, that reaches the mammographers. It's very promising direction. But I'm actually not going to talk about the cancer present or absent, because, sorry, I'm going to go back once the slide again, because, you know, whether cancer is present or not, it's like finding an apple in this picture that I showed you. You know, there is some structure that we know that's consistent with the apple. The same way in here, there are going to be structures in the image that are consistent with the cancer. So we know what we look for, and we can easily explain to someone, okay, there is the structure in this picture that well, that this is the cancer. What I'm going to talk next is more like the task that I mentioned about the happy sad picture, which may not be easily explainable. You know, what makes the mammography decide whether patients are at higher risk of cancer. So risk of breast cancer traditionally is estimated from the clinical parameters, from the clinical data of the patients, not related to imaging. I'm not going to go into depth of it. You know, this is a traditional way of doing it. But one of those risks is the breast density that we can determine based on the mammograms. So essentially, the breast density means that that the higher the density, like more connective tissue is in the breast, there is a higher risk of cancer. So this is a well-known risk factor that is actually used in the traditional estimation of the risk. And there are 4 categories, by American College of Radiology that grades those how dense can breast be. That A, B, C, or D. However, if we look at the images of those breasts within one category, we can see that, well, they can vary quite a bit. So that it's almost impossible to believe that if we look at, for example, category B, that's going to provide us the same risk with all those breasts. There's much more information there, and this information should be used somehow to estimate the better risk, right? So that tells you right away that what we do right now, in terms of the risk estimation, what was the current state of the art in the estimation of the risk of breast cancer, well, it has to be something better, So maybe AI will see something more than just categorize everything in category B. And before actually I tell you, and this was done, and I'm going to tell you a little bit about the results of this investigation. But before that, I'm just going to spend very little time to tell you about the measure, what was used to measure the performance, because that may not be obvious to everyone. Sensitivity and specificity, there are 2 measures that are used heavily in medicine. Sensitivity is, let's say we're trying to decide whether a patient has a cancer. So there is only yes or no answer. So sensitivity means, that if you have some number of patients that we actually evaluate this on, there are going to be some number of true positive patient, P. So if our algorithm, get 20 out of 40, then since our sensitivity will be 50%. And this is computed by, the number of true positive that, we have a positive case and we set it positive divided by the total number of positives. And then specificity, it's the same, but applied to negative cases. The very big problem of this is that, and connected with the artificial intelligence, machine learning, is that if you remember, the output from those networks is a number, is this what we call probability, number from 0 to 1. So if we get the number, so how do we decide whether the AI says positive, and how do we decide that the AI says is negative? Well, I mean, the most logical is to say, okay, let's take 50% and say if AI says more than 0.5, it says there is a cancer. If it's less than 0.5, it says there is no cancer. But there is no guarantee that this is actually optimal for our task that we do. And typically in screening, that's another good idea. So then what I'm saying is that in order to use sensitivity and specificity, we need to commit to some threshold of acceptance above which there is a positive and below is negative. And in data science, we don't want to do that, right? Because that actually just removes a lot of information on how algorithm would work if this threshold would be different. That's why we typically use this so-called receiver operating characteristic curve, ROC curve. And all the ROC curve is that it's drawn by saying that, let's take the threshold, and I show the threshold, for example, dt equal to 0, means that, and of course all the numbers that we get from the network are going to be more than 0. So we're saying all cases are positive, and then of course sensitivity is going to be 1, specificity is going to be 0, and then we change this threshold to dt equal to 1, and then for every threshold we compute 1 point on this graph, and that creates this curve. So essentially, and then we can, having the curve, we can measure the area that is under the curve, and that area would be representative how the algorithm works for sort of all the possible threshold that we can throw at it. And then higher the area under this curve, and that's always that is called AUC. Then the algorithm is better. And so with this introduction to the measures used in data science, I'm gonna just now tell you about the study of those risk, of determining of risk from images that was published in 2019. I chose this, one because, this area of AI where we look at the bet, when we look at the risk estimation is very interesting and very promising, but also because I wrote an editorial to that great publication that came from MIT and Mass General Hospital. So what they've done, they took the data from single hospital from MGH, and then they look at the cancer registry, and then they decide which mammograms were done, and they were normal. All mammograms used in this study were normal. Only, but certain part of those mammograms that they used were normal at the time the mammograms were taken, but then the cancer was actually diagnosed within 5 years of this normal mammogram. So now the questions that they wanted to ask is, well, we have a normal mammogram, but does this mammogram actually predict that cancer will develop within 5 years? So that was the task. And then the authors, took different models of prediction of such risk. And the model one, that's a traditional model based on the clinical data. And then they also built their own model based on the clinical data. Then they used only image. So they basically provided the normal mammograms and asked, is there going to be cancer in 5 years? And then they used hybrid, connected the deep learning on images and the clinical data. And these are the results. And what they concluded is that actually the image has even better information about whether cancer is going to develop or not. Normal image, normal mammograms without sign of cancer. And adding clinical information to image, improves a little bit, but not much. So that was pretty incredible result, very encouraging, to actually, when we think about this AI, about the potential of AI, how it can actually change healthcare. So that's what they discuss. That the information in those images is something that is more information about than the clinical factors, which is pretty incredible. Then the information is complementary. I already mentioned this, but the third point is something that I want to emphasize here. They basically couldn't figure out what makes those images be more predictive of cancer or not. They couldn't actually pinpoint this. So this is the same as a problem that I mentioned earlier when we look at the scene and we're trying to decide whether this is a happy or unhappy scene. Well, it's again, well, not really, for different people, maybe different things, and we don't really, have a good answer, what makes the picture unhappy. It's a very, very similar problem. So, and okay, sorry. Before I go to next slide, I want to just tell you that I have 2 more slides, and to tell you about something that gonna psych your mind. So if so far stuff that I haven't that I show you didn't, I'm hoping for the next 2 slides they will, then that will convince you that that those new techniques, they are pretty incredible. It's I just want to say that even 10 years ago, that was unimaginable to do things like that, to trying to get so much information from those images. We didn't know how to do it. We know it now. So let's see if I succeed. Obviously, I told you that, okay, so there is this great AI algorithm that from normal mammograms can predict cancer. So the question is, can radiologists do that? Can humans do that? And it's not that easy to measure this because, well, I'm not going to go into details because, but well, well, it's not easy to measure this because if we just show the mammograms to mammographer, he will do how the radiologists know how to read the images, and that may destroy actually the perception of radiologists whether this is if this is normal, whether this is going to develop cancer or not. So this experiment that was done by the group leading by Carla Evans from London, they essentially took 59 mammographers, and they showed them the mammography images, but only for half a second. So imagine the experiment. So the radiologist is sitting in front of the computer, and then the image comes into the screen. He sees for half a second, and then the question was, and all images were normal. Again, all mammograms were normal. They asked, is this patient with this normal mammogram going to develop breast cancer within the next few years? And amazingly, they came to a conclusion that radiologists were able to do that. They were not able to explain why, because half a second is time not enough to actually move your eye to something that you are interested in the image. You just process the images using the Gestalt view, the gist view of those images, and then just based on this, they were able to tell that. So obviously, the problem was that not the problem, but they were not able to tell why. They were able to do it, but not able to tell why. And actually, the performance in this was correlated with how long they were practicing mammography. So I think that this is pretty amazing related to it. And another study that I wanted to show you is a little bit different application. It's also radiography. It is an application where we look at the hand and the bones in the hand. But the actual task was different than some typically medical, that is done typically on those images. The authors of the study asked whether the image of the hand comes from a male or female. And they look into a very wide range of ages and amazingly, radiologists were not able to actually tell whether the hand is female or male. And they had two radiologists look into that. One had 58% accuracy, the other 46. So obviously 50% accuracy is given because their test set had 50% male, 50% female. So if you just randomly guessing, you randomly should get 50% accuracy on it. Where the AI got 96% of accuracy. So, well, that's close to perfect. Very interestingly, then they also tried to teach the radiologists, what to look for in those pictures, because the AI has some techniques that you can actually emphasize in the image what matters. It's not perfect, actually far from perfect, but they tried to teach the radiologists based on those techniques, and there was no improvement. So the conclusion of this was that, well, there is a there are tasks that we may actually see in the future that these algorithms will be able to fulfill, and the humans not, which is pretty amazing, you know. So before the talk yesterday, I mean, the finding of the study is so you know, say crazy that, you know, yesterday I contacted the senior author on that paper just to make sure, you know, if this is still valid, you know. But the study comes from Harvard. I don't know if that means anything to you, but it's typically a good science coming out of there. So, well, it is what there is. So to conclude that section, I think, you know, I hope I convince you that this AI is pretty amazing, you know, and it can get it can estimate the risk from mammograms pretty accurately. However, you know, the problem with this is that we at least for this task may not be able to tell, you know, why this risk is estimated as is, you know. And although I concentrated here on the mammography, you know, this is a generic problem that applies to many areas of using this deep learning in medicine. And so this basically raises a question, you know, are algorithms like that acceptable in healthcare? So are we going to accept those algorithms, you know, as is, without understanding, you know, why they give the decisions, just by knowing that they are right, you know? So I think this is a very serious problem, you know. Then it is known that people have a so-called algorithm aversion. So if they see that the algorithm is making mistakes, they stop believing algorithm faster than humans, you know. So if they see human making mistakes, you know, it's not that bad as algorithm making mistakes. So this actually, you know, creates a lot of challenges, and I'm gonna talk next week about it, you know, how to solve those, well, how to approach those problems, because, you know, that's Sano is a research institute. We research problem, you know. If we know how to solve them, that will not be a research institute. And I only want to say that that we, I think, you know, what's important is to develop trust in those solutions that we're gonna provide. You know, even if we don't understand them, you know, we as humans, you know, there are a lot of things around us that we learn to trust. You know, we drive cars 100 kilometers per hour on the freeway, and you know, not afraid for some reason. And so I don't know. I mean, we'll see in the future how this will go. I just put here, you know, the picture of from Star Trek Next Generation. You know, if anyone is into this sci-fi, where there is a doctor that has a tricorder. Tricorder is something that actually diagnose and treat diseases. I don't think that that physician understands how it works, but she knows it works, and, you know, audience actually take it pretty well. I think, you know, that's what there is. And is this the future? You know, for us, for healthcare? So I basically came to my third part of the presentation. I know it's very late, it's 9:03, but I just have one more slide. so I'm almost done. So the remaining question is when those inventions gonna actually affect and gonna improve what we have right now. And, you know, obviously when I was preparing this this presentation, and Marian asked me for the title, I put why, how, and then say, okay, when, of course, you know. So, but then I realized, you know, that I don't really know when, and I was trying to figure out what to do, since I don't know, I have not much to say. And then I remember that in 2009 I had a presentation for radiologists in Brigham and Women's Hospital, where I worked. And at that time I was 11 years younger, so I was less smart. So I ventured, you know, the estimations of when we're gonna see things in the future. And I'm just going to present to you as a last slide of the presentation, the slide that I also presented there. So the presentation was given in June 30th, 2009, and I said that, this is the picture that you look in 20 years, and the radiologists love this, obviously. I don't want to go into depth of the slide because this slide is going to be starting slide of my next presentation, where I'm gonna tell you, how we're going to do it and what areas we're going to attack. I just want to say, amazingly, that estimation was not that bad 20 years in advance, that we're going to at least, make life of radiologists better. But I'm just going to next week tell you also how we're going to also affect the general healthcare in Sano. Yeah, one thing for sure, if that's true in 10 years, the burnout of radiologists is going to be smaller if that picture is true. So with this, I would like to finish this presentation, and I'm happy to answer any questions you have. Thank you.
Many thanks for your talk. Many thanks for overview of all these problems which are related with and promises which are related with application of artificial intelligence in medicine.